Hi, my name is Connor Frock, and today I'll be giving an informative presentation on carbon capture and storage technology, which is a piece of the clean air puzzle. So with our continued reliance on fossil fuels, air pollution has become one of the largest issues of the 21st century. And despite some efforts to reduce our emissions, it's ultimately looking like we're not going to be able to reduce our emissions in time before it's too late and the dramatic effects of global warming take place. And that's where carbon capture and storage could potentially bridge the gap between now and a future low carbon economy. The premise of carbon capture and storage is basically applying it at any plant that emits a substantial amount of CO2. It'll scrub the air and capture the CO2, and through transportation by pipelines or other methods, we could inject it deep underground into a porous rock formation where it is trapped and stored. So an overview of this presentation, first we'll be going over the Paris Agreement and implications of not achieving the goals set there. I'll put the agreement into a perspective and discuss the carbon budget and what remains of the carbon budget. And then there's also some solutions available there. I'll be evaluating the following carbon capture technologies, which entail post-combustion, oxy-fuel, and pre-combustion. I'll also be discussing the debates on carbon capture and some current obstacles facing carbon capture, and then I'll sum it all up at the end. So, the Paris Agreement was basically a commitment to limit post-industrialization global temperature to no more than 2 degrees Celsius. And on December of 2015, nearly 200 countries signed this legally binding agreement. Now, how did we come to this 2 degrees Celsius benchmark? Well, a Yale economist known as William Nordhaus, which interestingly enough, he's an economist and not a scientist, but he decided science alone can't dictate this benchmark, but it also depends on society's values and current technology. So, in conclusion, he decided a reasonable benchmark would be a temperature increase that one would observe from the doubling of CO2 levels from the pre-industrial era, which equates to about a 2 degrees Celsius increase. Now, the implications of not reducing our emissions in time and witnessing a 2 degrees Celsius increase would be a much warmer world, increased ocean levels, and agriculture, infrastructure, weather patterns, as well as the world economy would be dramatically affected. So when discussing the carbon budget that was created during the Paris Agreement, right now the world has anywhere between 600 and 800 gigatons of CO2 emissions left in the budget this century, according to Carbon Crunch. Currently, we are emitting a little over 42 gigatons of CO2 emissions each year, but that number could actually still be increasing due to population growth, continued dependency on fossil-fueled power plants, and not utilizing renewables fast enough. This analysis basically means the world has less than 8 years to achieve net zero carbon emissions. If you look at the graph on the left, it's basically 4 different projections based off of when we peak our CO2 emissions. We already missed this deadline, but if we were to peak our CO2 emissions in 2016, that would have allowed a 25-year transition till we finally get to net zero carbon emissions. Now, and the reason why I said it's not looking like we're going to achieve this quick enough is because we're heading in the direction of peaking our CO2 emissions around 2025. And based off that line, it's showing we have a little less than a decade once we peak our CO2 emissions to transition to a net zero carbon economy. It's not looking like we're going to have enough time, and utilization of carbon capture will become more and more vital. So the Department of Energy predicts renewables will only grow to about 14.7% of our total energy needs by 2050. Fossil fuels, looking at that trend on the next figure on the left, fossil fuels stays very prominent. At the end of the day, fossil fuels are not going anywhere, so we're going to have to start implementing carbon capture now. Um, so we need solutions, and these solutions need to encompass all three aspects of CO2 reduction: renewable growth, energy efficiency, and carbon capture and storage. So now I'll start talking about the three primary technologies for carbon capture and storage, and there's actually 3 videos that walk through each method, and I'll give a technical overview of each one. So the first method is post-combustion, and its largest benefit is the ability to retrofit this process to any pre-existing power plant. And it's basically taking the air and fuel is then combusted into a boiler. Steam is a byproduct, which is used to power turbines or other electricity. And then in the remainder flue gas, the flue gas is ran through a chemical wash, which is basically a packed column with the solvent monoethanolamine, which will strip the CO2 from the gas, and through compression and dehydration, the CO2 is ready to then be transported and stored. So when talking about pre-combustion, this method has its benefits as the carbon dioxide is captured before it is combusted. So first, the air is denitrified through an air separation unit, and using pure oxygen, you can add the fossil fuel into a gasifier, which creates a syngas mostly consisting of carbon monoxide and water. Now, through a gas shift reaction, the CO2 and hydrogen is created, and from there the CO2 is ready to be compressed and dehydrated and is ready for transport and storage. The hydrogen, like other processes, can then be used to power gas turbines and other electricity. And the main importance is now, once the flue gas is emitted into the atmosphere, it contains no harmful global warming gas. So the last method is oxy-fuel combustion, and this method might be the most efficient as it captures the highest concentration of CO2 between 80 and 98%. So first, the air is ran through an air separation unit again, where it is denitrified. The fossil fuel is added into a boiler where it is combusted in pure oxygen. So in turn, steam is produced, which is used to power turbines and other fuel sources. CO2 and water is produced, which is also recirculated through the boiler to control its temperature. But after that, the CO2 is captured, compressed, and ready to be transported and stored. So while I was talking through the steps of each process and how it exactly happens, I was kind of talking about the advantages of each one, but now I'll go into a more black and white explanation of each one and the impacts of them. So with post-combustion, it's the easiest technology to retrofit to existing plants, and it is the only feasible option for existing coal plants. It's the most efficient technology in terms of energy to gigatons of CO2 emissions, and the low concentration of CO2 at the point of separation, so after it's combusted, makes this technology more expensive. With oxy-fuel combustion, it has the highest concentration of CO2 at any point of separation, which is 80 to 98% of CO2. The remaining particles can be removed through electrostatic methods. Oxy-fuel combustion also consumes large amounts of oxygen, and the air separation unit, like I said, is very costly. It's difficult to retrofit to existing plants. It has the highest energy penalty of the 3 technologies, and this one also has the least amount of research and commercial success of the 3 technologies. Pre-combustion has a higher concentration, like oxy-fuel, of CO2 at point of separation. This technology can actually be retrofitted to natural gas plants very easily, and commercial solutions have been successfully deployed. and it has the lowest energy penalty of the three technologies. So right now, there are about 22 operational carbon capture and storage facilities around the world, most of them being pilot projects. And there just hasn't been too much utilization of carbon capture due to lack of funding and investment. So here's what some of the criticism is saying. People are worried it'll just expand our oil production, it'll provide a lifeline to a declining coal industry, and ultimately just further enable our reliance on the fossil fuel economy. Also, storage is difficult, if not impossible, to monitor. So once the CO2 is injected deep underground, it has the potential to leak out back into the atmosphere. So we have to figure out a system to be able to track and monitor that. Carbon capture also just requires more energy for the separation process. So we need to burn more fossil fuels and able to capture it. There's also, so right now in the US, there's about 4,000 kilometers of CO2 pipeline. We would need to increase that number dramatically to make CO2 capture accessible to all power plants. So, in conclusion, the world has simply run out of time to be 100% dependent on renewables. The solution must include all three key things, including efficiency, renewables, and carbon capture. The oil and gas industry is large enough where if they wanted to implement this carbon capture and storage system, they could make it happen relatively quick. The carbon clock is not stopping, and the problem only gets more and more difficult each day. The US and the world need to stop ignoring this issue, and we need a "we will go to the moon" type of speech and commitment is needed from world leaders if our planet is to be protected. So overall, we have the technology for carbon capture. We have ways to implement this process to existing plants and new plants. It's a matter of will at this point. Now there's no single solution to completely reducing our CO2 emissions. However, carbon capture and storage is the largest of many solutions.